So this is objective 5.3, applications of exponential function. Today our study is going to be specifically, and I have to yell because I'm walking away from my computer, exponential decay. Okay, tomorrow we'll do exponential growth. So your objectives, you will be able to solve exponential function application problems, real life problems for radioactive decay, oceanography, which really is more a study of how light travels through water, the Malthusian population growth, the Malthusian theory, and epidemiology. The last three are all examples of growth, and the first two are representations of decay. So we're going to break it up over 2 days. So let's start with just a brief explanation of what we're working on. A mathematical description of an observed event is called a model of that event. Think about it. In science, you do experiments and you observe what happens, right? Yes. And then you record your data. And then you take that data and you put it on a table or you put it in a graph and you use math to interpret your results. And then you can use math to make predictions about what's going to happen. So this is just an explanation of the math that goes with the experiments. Many events that grow or decay over time can be modeled by an exponential function. In the form y is equal to the function of t, or the function of time, on some times action on whatever it is that you're observing. And it's equal to the equation a times b raised to the k times t power. So ab to the kt. Get it tattooed on your brain, AB to the KT. Okay, where A, B, and K are constants and T represents time. Time is the thing that is relative and it will change. Okay, so if the function is an increasing function, we say that y grows exponentially. If your function is a decreasing function, we say that y decays exponentially. Okay, so today our focus is going to be examples of exponential decay. So we're going to start off with radioactive decay. How an element, a radioactive isotope or element, how it decays in a half-life. Now, the definition of a half-life, are you ready? Is the time it takes for half of a sample of a given radioactive element to decompose. Basically, it's how long does it take half of that element to break down and become something else, a different element. Okay? So the example that I put up on the board for you is the decay of carbon-14. And carbon-14 is used to date how old something is. So if you're talking about fossils, you can measure how much carbon-14 is in that fossil and determine how old that fossil is or at what time period it was alive, because when we're alive, we take in the carbon that is in our environment. And during Earth's life, there are different amounts of carbon in the air. Did you know that? Anyways, so carbon 14 has a half-life of 5,730 years. So this isn't you can see the exponential decay. Look at how that's curving. It starts out with a really deep decrease, and then it starts to level out. So we start out at a time. This is our time here, and this is the amount here, okay? Over half-lives, over one half-life, or over 5,730 years, 10 grams of carbon will decompose to only have 5 grams left, and the other 5 grams have turned into some other elements. And then after another half-life, another 5,730 years, it becomes 2.5, and then becomes 1 1/4, then becomes, and it breaks down, until at some point down here at 1,000 half-lives, it's at a trace, right? But it's still not nothing. There's still a little bit of carbon-14 in it. So definitely an example of exponential decay. So let's take a look at a problem. Now, this says half-life. So it's interesting that it has a half-life, and in the formula over here, you see base 2 raised to a negative power, right? What's 2 to the negative 1? 1/2, right? So this base here raised to a negative power is telling you that you're going to be dividing by 2 all of the time. So the base 2 is coming out of a half-life. If I wanted a third life, what would our base be? 3. If I wanted a fourth life, I'd use the base 4. So in half-life, you'll always see the base 2 in the equation because it's a half-life. Okay, and it's exponentially decaying, so of course you raise it to a negative power so that it breaks down instead of builds up. So let's take a look at our formula over here. We'll break it up and then we'll solve this problem. So I'm going to color code. I'm going to call A. You don't have to color code if you don't want to. Okay, I'm going to color code. A, this representation of A up here, is the amount remaining after time, okay, over time, over 10 years, over 15 years, over 1,000,000 years, whatever the time is, how much is left, the remaining amount. A sub 0, sorry, that's A sub 0, is the amount at 0 in time. So that's the starting amount or your initial amount, okay, initial, but it's at time 0. No time has passed. It's your starting amount. And then T, I'm going to do that in red. T is your time. And watch the units because you'll be doing half-lives of different things. You might have to define the half-life of nicotine in your system, not your own personal system. Please don't smoke because that's bad for you. But it has half-life of hours, not days, not months, not years, but hours. Okay, so just pay attention to that. Each element has its own half-life. And then H is going to be the half-life of whatever element. And we will be given that information. You don't have to come up with it. Okay, so you'll be told that information. So my color code. All right, so we're going to start by reading the problem here and annotating the text. It says the half-life of radium, okay, radium, is approximately 1,600 years. And is it okay to approximate something that has a half-life that's that long? Yeah. Right? Because what does it matter if it's 1,605 years? Right? That's a long time. Who cares about 5 years when you're talking about that much time? Okay, so that's our H. Okay, and then it says how much of a 1 gram sample, well, what's the 1 gram sample represent? Your initial, right? Your A sub 0 will remain after 1,000 years. So what's 1,000 years representing? Time, right? That's our time. So we have an A sub O, a T, and an H. And the question says, how much will remain? So that's what we're looking for, right? And that's our A, our remaining amount of radium. Okay, so we're going to write our formula. We're looking for A is equal to 1, right? So 1 gram times base 2, because it's a half-life, right? And we're going to raise it to a negative power. And then let's see, we're going to plug in what goes on top, time. So that would be 1,000 over half-life, which would be 1,600. Okay, so there's our formula. There's our equation that we're going to plug into our calculator. And I did ask you to get your graphing calculators today because I would like you to know where to find the fraction, because it's not as simple as our other little calculator, but tomorrow we have to graph things, so I want you to have to just use one calculator, okay? So with your graphing calculator, I would like all of you to type in 1 times 2 carats. Come on, guys, you need a graphing calculator. You got to be able to do this. Let's go. Okay, I'm going to pause the video. So to put the exponent in as a fraction, again, it's alpha, y equals, enter. And that'll bring you the fraction. And you can type in negative 5/8 actually, because if you reduce 1,000 over 1,600, you can bring it all the way down to 5/8 if you want. You're going to get the answer approximately 0.648. What? Give me one more. 4. Does it round to 5 or does it stay at 4? 4. Okay, so I'm going to give you tips today that I suggest you write down in the margins. When we're working with exponents and logs, we round to 4 decimal places, especially when we're dealing with such a small amount. So we're going to round to 4 decimal places, and then we're going to answer the question. So how much of a 1 gram sample will remain? I think we could say approximately 64.84% of 1 gram will remain. Or you could say 6,484 hundred-thousandths of a gram will remain, if you'd like to. But I think logically, 64% of it makes sense. About 64% of that 1 gram will remain. Okay, you do the next one by yourself. Check. After 800 years, how much radium will remain? So you could have plugged into your calculator 2 to the negative half, because 800 is half of the half-life, and you should have gotten the answer, 0.7071, or approximately 70.71% will remain, or 0.7071 gram of a gram will remain. Okay, so there we have one example of exponential decay. And now we're going to move on to the next example. We're going to be studying how much light can travel through, well, the intensity of light. How much can you see as it travels through different parts of the ocean? So the intensity of a light source is an example of, look at here, what do you see? Exponential decay, right? So this is not something that's in your notes. It's just something that I add that's supplemental. So if I were to take, for example, you've played with flashlights before. You know that your light, when you're looking straight at it, is super intense. You don't want to put this straight on your eyeball. And the further away you are, the more diffused the light will be. But the closer you get, the more intense the light is, because the rays aren't spreading out. They're all concentrated on one spot, right? And the further away you get, the more the rays, like in my example there, spread out and the light isn't as intense. So we're going to be studying the intensity of light. Okay? So the source, like for example the sun, be really super intense. If you were close to it, the light would be so intense you'd burn your corneas. But the further you get away, the rays of light, of course they travel in, light waves, but still the waves travel in these straight lines, and the further out they get, the further apart they get, and the more diffuse the light is. Okay, so we're going to study that, and we're going to study it specifically how light travels through water. So here we have the problem. The intensity of light measured in lumens at a distance of x meters below the surface of a body of water decreases exponentially according to the formula I equals I sub 0 k to the x power, where I sub 0, I think we can just mark this, I sub 0 is the intensity of light above the water's surface. So we can say I sub 0 is intensity at the source, which is going to be 0 inches away from the source, just right as it's coming out of the light bulb. Okay, so that's going to be our at the source at 0. This is at 0 distance, no distance at all. Okay, and then our I will be the intensity at a distance away. Okay, how far? It's our intensity at a certain distance away. And we're going to be also talking about K, and K is the constant that depends on the clarity of water. Because of course, if you're looking at really clear water, then the light's going to be more intense. But if it's cloudy and it's got a lot of little pieces of sediment floating, the light's going to bounce off that sediment, and it's not going to not as much of the light's going to reach down very far. So K, of course, you have to test the clarity of the water, but the problem, it tells you what it is, so you don't have to worry about that. Okay, so K is the clarity. I keep doing that. Clarity does not start with a K. The clarity of the H2O, or whatever the light is traveling through. It's your constant, it's your base. Okay, so this is your base of your exponential. And then X is your distance from the source. Okay, so as we read through this problem, we've kind of marked it up here. It says, for a certain area of the Atlantic Ocean, the intensity of a light at the source is 12 lumens, whatever that is. I don't know how intense that is. With our K, or our clarity of our water, being 6/10. And I don't know if that means it's really clear or it's muddy. I don't know. Find the intensity of light. That's what we're looking for, right? At a depth of 5 meters. So that's our distance. So how deep? All right. So we're going to take the equation and we're going to plug it in. So we have I, intensity at 5 meters is equal to the lumens, which is 12, times the clarity, which in this case is 0.6, and we're going to raise it to the 5th power because that's the distance. And so you can see here that it's exponential decay And why is it exponential decay? Look at your base. Your base greater than 1 or less than 1? It's less than 1. So when your base is less than 1 and you're raising it to a positive power, it's decay. Okay? So plug that into your calculator. To 4 decimal places. So that looks to me like less than 1 lumen intense at 5 meters. So I could say lumen at 5 meters. I could say, well, why don't I just say it's a little bit less than 1 lumen? I could say that. That would be an acceptable answer. And then you try the intensity at a depth of 10. Okay, and so you should have plugged that in and got the answer 0.0725. Is it 25 or 26? 25. Lumen at 10 meters. Or what would be another acceptable response? Less than 1/10 lumen? Okay, so today we're going to stop there today, and tomorrow we're going to study exponential growth. Your assignment is to do 3 through 9 odd, and 13, 14, and 31. And if you want some extra practice, 4 through 10 even, extra credit. 5 rounds to the 6. There, I fixed it.